All right, welcome back. And so in the last video, we looked at the mean value theorem, and now we're going to extend that via the extended mean value theorem that Cauchy developed. And so the problem statement is here. So now we introduce two functions in here, which are differentiable on the open interval, continuous on the closed interval. And so that's just a little bit of an extension, right? Differentiable, you get continuous on the open, and then you just have to check the endpoints to make sure that they extend in a natural way, that they don't jump or anything like that. And so here we also just need to check that g prime is not 0, because as you can see we have a denominator, so we just need to make sure we're not dividing by 0. Okay, and so then we get that the ratio of the IROCs, the instantaneous rates of change, are equal to the ratio of the average rates of change. So just the same idea as what we saw before, just now we have two functions to work with. Okay, and so if another kind of side comment, so why is this considered an extension? Because if we let g of x be x, right, then the derivative is 1, and we just get the same thing as what we saw in the mean value theorem in the first video. Okay, and so generally this version I haven't had to use in all that often, but we just want you to be aware of it. And so to use this, we might consider a scenario where we have like the unit circle, right? When we look at this equation, that is a unit circle. Okay, and so we want to use the extended mean value theorem to show that there exists a C between -1 and 1, so that the conclusion applies. Okay, and so so here, why we can't use the mean value theorem is because the mean value theorem it works with just one function, right? And so it has to pass the vertical line test. If we use one function for the unit circle, well, it's not going to be a function, right? It fails the vertical line test. Okay, and so we need to work with something else that can represent that function, or that relation, I'll say. Okay, and so what we're going to do is we're going to work with the unit circle's parameterization, cosine and sine, and I'm actually going to switch these just because we run into an issue. So I'm going to call this y and this x. Or sorry, nope, I'm going to leave that as x and y. I'm going to replace these and call these g and f. Okay, so it's more like y over x idea when we do the extended mean value theorem. Okay, so then, okay, I can calculate the derivatives like g prime. I'll do this in blue. So g prime is equal to negative sine of theta, and then f prime is equal to cosine of theta. Okay, so given that they're both differentiable, right, I can find the derivatives and they exist on that interval. I think I've satisfied that condition, right? Continuous, yeah, they're trig functions, right? They're going to be continuous on their their sine and cosine. They're going to be continuous on their domain, right? And then the only thing we have to think about is what are a and b. Our first idea would be to do 0 and 2 pi, right? But then we have to remember that g prime can't be 0, okay? And so if we think about this, sine of 0 is 0, right? So I can't use this, at least that endpoint, and then 2 pi. Sine at 2 pi is also 0. So I need to shift to something that'll make g prime not equal to 0. And so I think instead of this, right, I can't use that one. I know that minus pi over 2 to pi over 2 would be okay, right? At the endpoints, g prime would be 0, right? But I'm not including the endpoints to satisfy the hypotheses of the EMVT. Okay, so then let's look and see what this says. Okay, so I'm going to say by EMVT, what do I get? So I get, let's see, it was f prime, so it would be cosine at c. Let's write that neater. Cosine at c over g prime at c, so this would be negative sine of c, okay, and this is going to be equal to, and then I'd get f, let's see, so it'd be f of b, so it'd be, let's see, so it'd be sine of pi over 2 minus sine of negative pi over 2 all over cosine of pi over 2 minus cosine of negative pi over 2. Okay, and now you're probably thinking, okay, that denominator is not looking good because I get 1 minus a negative 1 over 0 minus 0, so then I get, 2 over 0, okay? And the left-hand side would just be negative cotangent of c, or we can just move the negative to the other side and say it's cotangent of c is equal to negative 2 over 0. But so we get cotangents undefined, right? And so, okay, this isn't, we might think this is a problem, but it actually isn't, right? So as we think about this, what does this mean? Okay, where is x over y equal to, so cotangent, or sorry, let me change the problem. Negative 2 is just a scaling. So if we think of this just as cotangent of c being equal to 1 over 0, this is x over y, right? Where does that happen? Well, at the point 1, 0, right? So that means that c, so that implies that c is equal to 0, okay? So we can find a c, and that allows the extended mean value theorem to work, right? So here, this is just an example of the extended mean value theorem. And again, you would use this in scenarios where maybe you don't have the hypotheses of the original mean value theorem satisfied, where you don't have just one function that's differentiable. And so here we had the unit circle not being differentiable. We split it into two functions that were differentiable via parameterizations, and then we could use the extended mean value theorem.